So what is a rational function? It's basically a function made up of polynomials, a polynomial divided by another polynomial. But being a polynomial in the denominator, oops, I want that, I want this. Having a polynomial in the denominator, that means there's going to be some value of x in the denominator. And x is a variable, so it's possible to have a variable that makes the denominator equal to 0. But that would be undefined. So it's important to realize that we have restrictions here. The denominator cannot be 0. Here's a couple of examples of what rational functions look like. 1 over x. Notice how it's broken here. Here's another example. 1 over x squared. There's kind of a break here. We're going to talk about these breaks. Those are called asymptotes. Here's another example. And there's another break. It kind of splits the function right here. These are called asymptotes. So it's typical of rational functions to have those broken places creating different branches. If there's one break, you're going to get 2 branches, but sometimes there's 3 or 4 branches depending on how complicated it is. All right. So, because we have these breaks, there are some limit behaviors that we want to explore. And this particular function has a problem. Well, let's not talk about that yet. Let's talk about the tails, the end behavior. Now, polynomials, their tails always go to plus or minus infinity. So polynomials are always going to be up forever, down forever, or they may have that chair kind of behavior. So one tail is down to infinity, or down to negative infinity, and one's up to positive infinity. But in rational functions, for the most part, their tails are not going to go to infinity. They're going to approach something called a horizontal asymptote. And I want to explore this behavior here. We call that a horizontal asymptote. More on that later. But what I want to focus on is this tail. That function, I'm going to change the color for that. The function is going to continue in this pattern forever. And so we can describe the limit behavior. So x is getting bigger and bigger and bigger and bigger, and as x gets to infinity, y is approaching 1. You can see between we've got between 0 and 2 here. It's kind of landing in the middle. But what happens when x goes the other way? X goes this way. X gets bigger and bigger and bigger. Each time x gets bigger and bigger and bigger, y's are coming up, 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 but they're leveling out. They're leveling out also at 1. So the end behavior here is described as y going to 1. So we've seen this notation before when we were talking about our polynomials. But now we're using it slightly different on these rational functions. So the end behavior is not going to infinity, it's going to a constant. Now, occasionally they will go to infinity, but most of the ones that we're going to deal with will approach 0 or some constant. However, there's another aspect to rational functions which involves the denominator. Remember we said, I'm going to change colors for this part of it. We said that the denominator can't be 0. Well, if x plus 2 equals 0, the fraction's messed up. So if x equals negative 2, that is going to mess up my function. So we would say that the domain is all real numbers except x cannot be -2. And so the effect of that is at -2, there is no output. It's just empty. It's a hole. There's nothing there. It's not. I didn't mean to say hole. But it's broken. There is a technical hole that we'll study later. We show that the graph is broken with these little asymptote marking lines, but there's nothing there. At -2, there is nothing in the graph. And then what is the graph doing? Well, the x's are approaching that -2 value, and as the x's approach the -2 values, the y's are going higher and higher and higher and higher. So these y's are heading up to y of infinity. So as x approaches -2, y is going to infinity. But wait, on the other side, something different is happening. On the other side, if I approach -2 going this way, as the x's approach -2, the y's are going down, 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 down. So the y numbers are going down to -infinity. Now this is a little bit of a dilemma. When we look at this, there's a tail that goes up and another tail that goes down. And so if we use this arrow notation to describe our tails, we have a little bit of a problem, because x is going to the same number, but the outputs are different. Now we're going to have to differentiate how we communicate that. And so we're going to add something to the notation here. I'm going to say x going to -2 from the right. Now I'm going to put a little plus sign on it to say I started x's from the right side. And so x's are going this way and the y's are going up. So x is approaching from the right. On this other one, I'm going to say it slightly different. I'm going to say as x approaches -2 with that little minus. So the plus and minus here, they look like exponents, but they mean something different. They're saying that I'm approaching it from the left. So I'm approaching -2 from the left. As x goes to -2, that way the y's are going down to infinity. So we need to add this little notation here to talk about the tails. Now these are a new kind of tail. They're tails at the asymptotes. So in general, we would say as x goes to a number, I'm just going to say a with the plus sign on it, that means x approaches a from the right side. And as x approaches a with a little minus as an exponent in the exponent spot, it's not an exponent, but it's a notation that says x approaches a from the left side. So this is a slight adjustment we're going to do to our tail behavior. But also to include here, remember or understand that when we do rational functions, now we have tails at end behaviors and at the end, and we also have tails at these things called asymptotes. All right, so I want you to be able to look at functions and describe these tails, these behaviors. Let's practice this.